Hello, so this is a revision video for OCR A-Level Chemistry 2.1.2, Compounds, Formula and Equations. This is a revision video, so only the essentials are covered for revision. For deeper explanations and for video lessons, please check the links in the description below and visit chemistrystudent.com. Ionic formulas showed a ratio of ions within an ionic compound. To write the correct formula of an ionic compound, the total positive and negative charges from each ion must balance out. We can usually predict the ionic charge for an ion of an element from its position in the periodic table. Group 1 metals form positive 1 ions, Group 2 metals form positive 2 ions, Group 6 nonmetals form negative 2 ions, and Group 7 nonmetals form negative 1 ions. This is based on the idea that the atoms will lose or gain electrons to get a full outer shell. Transition metals can have variable charges, which we can represent using Roman numerals in their names. For example, a name that includes ion 2 means it has Fe2+ ions in, and a name that includes ion 3 means Fe3+ ions. The ability of transition metals to form different charged ions and the reasons why certain ions exist is covered later in the course. Polyatomic ions contain more than one atom, and the bonded atoms share an overall charge. At this stage, you should be comfortable with the following polyatomic ions: a nitrate ion, NO3-, carbonate ion, CO₃²-, a sulfate ion, SO₄², a hydroxide ion, OH-, and an ammonium ion, NH4+. When writing ionic formulas, we must balance all the charges so the total charge is 0. For example, when sodium and chloride ions come together, to give no overall charge, the ratio of ions will simply be 1:1, given NaCl. Ca2+ ions combine with chloride ions, however, now the ratio would be 1:2, because the 2+ charge of the calcium needs to be cancelled out by 2 negative charges from 2 chloride ions, so the formula would be CaCl2. When a polyatomic ion appears more than once in a formula, we enclose it in brackets. For example, MgOH2 tells us that we have one magnesium ion with a 2+ charge and 2 hydroxide ions with a -1 charge each. When writing chemical equations, we must make sure they're balanced so that the number of each type of atom is the same on both sides. This is because we can't create or destroy matter during chemical reactions, so whatever total number of atoms you start with in the reactants, you have to end up with in the products. Ionic equations are used in chemistry to show only the species that are actually involved in the chemical change. Sometimes in reactions, there are ions in the reactants that don't actually change during the reaction. For example, if you react hydrochloric acid with sodium hydroxide, you make sodium chloride and water. HCl plus NaOH goes to form NaCl and H2O. Interestingly, however, if we look at this a little bit closer, HCl in water dissociates into H+ and Cl- ions, and NaOH also dissociates into Na+ and OH- ions. So this means on the left we start with H+ ions, Cl- ions, Na+ ions, and OH- ions. While on the right, sodium chloride exists as individual ions in solution, Na+ aqueous and Cl- aqueous, and water exists as just water, H2O. We have Cl- and Na+ in the reactants, and Na+ and Cl- in the products, meaning they don't actually change or take part in the reaction. We call these spectator ions, and we can remove them from the ionic equation, meaning we are left with just H+ plus OH- going to form H2O. This would be an example of a net ionic equation. We also see this in precipitation reactions.